But I'd like to welcome everyone here. I am with Dr. Derek Riley from Milwaukee, from MSOE. I'd like to thank Ms. Stone, who reached out to Dr. Riley and set up this presentation. So what Mr. Riley or Dr. Riley will be presenting on today is AI. So that's kind of a word that's thrown around a lot these days, right? Even me, I'm not really quite too sure what AI is. But we have a very distinguished professional here to tell us what AI is all about. And I will pass it over to him.
Excellent, thank you. Thank you for all coming. I'm really encouraged to see that the reluctance to sit in the front row persists at any age. It's great. This is my classroom. The students wouldn't be sitting in there either, so that's great. But thank you for coming today. This is hopefully going to be a fun discussion. I don't want this to feel too much like a lecture, but I have lots of slides and things to discuss, and then we'll have some time for Q&A at the end. But if you've got questions, can't hear me, you have anything comes up, feel free to raise your hand and shout out. So the title of the talk is the what, how, where, and why of AI. So I'm going to start with a quote, and this is a quote from Marvin Minsky. He said in 1966, he was one of the early founders of artificial intelligence. He said, artificial intelligence is when machines do things that humans are assumed to be intelligent to do. You'll notice it's very carefully worded, so this is a very loose definition, but this is really artificial intelligence. I hope you take it away from this discussion. It's a really, really broad field. It's been around for over half a century at this point. The historical evolution of AI is part of the intrigue of why it's suddenly become very, very relevant today. There was visioning done back by the early founders of AI concepts that is finally coming to pass half a century later now. And so this is part of the excitement. So let's talk about what is intelligence. If you put intelligence into Google, you'll get a definition that looks like this. It says the ability to acquire and apply knowledge and skills. Those are really important words. So we not only are acquiring knowledge, but we're also applying that knowledge. It's not data. It's not information, it's knowledge. So, you'll see synonyms like judgment and reasoning and understanding and comprehension. These are likely things we can all resonate with, right? Those are all sort of related to the concepts of intelligence. We use intelligence to make decisions. And so it can be easy to conflate the idea of making decisions with an artificially intelligent system. And often those are paired together. But the reality is an AI system is about acquiring knowledge, acquiring and applying knowledge. And then how the decisions are made based on that knowledge is an engineering task. It's actually not necessarily an AI task. And so, so I'll try to sort of strike that balance about the difference between understanding and generating knowledge and then making decisions based on that knowledge. And we're going to use sort of the human analog because we can relate to how we've acquired knowledge. And in a lot of ways, we actually designed AI systems in the spirit of the most intelligent beings that we know ourselves. So if we're going to try to design something like ourselves, it turns out to be, we're really complicated, and this is not an easy thing to do. But first I want to ask you the question, do you think you've used something that leverages AI today? So maybe, probably, right? And I hopefully will convince you the answer to that is yes. So if you've got an email, a text message, a phone call, all of those go through spam filters and checks. They go through suggested responses now. So if you have a smartphone or an email account, often you'll get little suggested responses that come back. Those are completely AI driven. So there's information about what you've typed in before, what other people have used, and that's what drives those. If you've read anything in the media, including a newspaper, even though it's on print, doesn't mean it hasn't been influenced by AI. Today, an informal poll of the authors of news stories has revealed that many of them use tools like ChatGPT to help them in actually writing their stories. There are tools that prioritize stories for different people. If you're consuming media online, Weather is a great example. We all complain about weather prediction. The reality is AI models have been attempting to predict the weather for a very, very long time. Centuries, you could make the argument. They've gotten more sophisticated, and yet weather prediction is still sort of an elusive thing to get right. In the medical space, AI has had some pretty significant impacts. Whether it's medical image interpretation, there's a lot of fantastic innovation in that space. Delivery of care, research into drug discovery, training avatars, all sorts of things there. You may have a digital assistant in your home, whether it's Alexa or Siri, Cortana. There's a bunch of different versions of this where you can talk to it and it will tell you the weather, it'll tell you the news, it'll turn on the radio. All those things are using voice recognition patterns that are entirely driven by AI systems. Your financial systems are all very heavily leveraged in the AI space. So whether you deposit a check on your phone, if you use a credit card, that transaction gets sent through a system that's looking for anomalous behavior. Are you buying gas in 2 different states within 15 minutes of each other? That's probably a bad sign, right? So there's all sorts of things that that are happening behind the scenes. You have no idea that are trying to prevent fraud, trying to understand, how to better manage portfolios and that sort of thing. There's a fair amount of innovation going on in that space. Of course, there's a lot of publicity around self-driving vehicles. I'm going to actually use that as an example and kind of talk through how that works. Heard a lot about cars that drive themselves and other sort of safety-oriented features that come out of that. A similar example are aircraft. So we've had autopilot systems in aircraft for decades now. In fact, most commercial aircraft can take off, fly, and land without pilots. And yet we still have pilots in the cockpit. Why? Well, there's a bunch of good reasons. We're in a safety critical system that we need humans to be involved in. So that's part of the engineering of the system, is understanding what the limitations of the intelligence systems are so that we can ensure that we have an appropriate margin of safety there. And then, of course, social networking is another really widely influenced area of artificial intelligence, whether it's feed prioritization, facial recognition. There can be all sorts of sort of entertainment aspects of this, and this is basically what I could fit on a slide. There's all sorts of other examples. So hopefully at this point you have the sense of, yeah, I've been influenced by AI today, and probably for quite a long time this has been going on. So let me talk about the difference between human learning and machine learning, because that's the kind of machine learning is another term that's used for artificial intelligence systems. So the field of human learning is called cognitive science. The field of computing learning is called computational science. So this is the difference between animals learning things or computers learning things. And so I always like to say that you can train a dog to do something your computer just can't do, right? There are things in the physical world that humans are always going to be better at, and then there are things in the computing world that we can design computing systems to be better at than humans. And sometimes those are not always obvious. The way that these systems learn, in a biological world, we have the concept of evolution, right? Where biological systems are adapting to their environment, right? We could reanimate a dinosaur today, and it's not going to behave the same way it did as 40 million years ago, because it's in a different environment. It has to adapt to that environment. And so the same thing with a machine learning task. We have to design these systems for an environment that they're built for. So there's definitely overlap between all of these aspects, but it's important. It's an important distinction that we're really not leveraging the concepts of evolution for the most part to build AI systems. There are some that derive that, some inspiration for how they work from evolutionary systems. I promised some history, so I'm going to take a little walk back in time here. The earliest concepts of artificial intelligence actually started in the 1940s. That's, I guess, the clearest line we can draw back. So the earliest founders, McCulloch and Pitts, talked about what's now called good old-fashioned artificial intelligence. So GoFi, and there were you may have seen a movie that came out a few years back about Alan Turing. He was one of the British mathematicians who helped in the Enigma machine, and he was also one of the earliest innovators in the space of artificial intelligence. He proposed this concept of a Turing machine, and a bunch of other innovations that are really, really impactful. But some of his research actually still persists today. But probably, one of the most important sort of hallmarks of this early time was a meeting in 1956 in Dartmouth, where the term artificial intelligence was actually first coined, or it was at least traced back there. So that was really sort of a decision by a bunch of researchers at that time who decided that was the right term. So I have a chart at the bottom here that you can sort of see. There have been boom and bust cycles in the world of AI. So the 1960s, which is basically what I just brought you up until, was sort of the first boom cycle where we this was the post-war era. Things looked like, hey, we have all these new intellectual concepts that we can apply to these things, right? The Enigma machine demonstrated that we could build a large complex computing system to solve a problem. And that opened up the possibilities for a lot of things. The problem was our world wasn't ready for that yet. So we could build big complex systems, but they were unreliable. We didn't really have enough data to feed them, and they were really power hungry. And so it just wasn't ready for us to leverage the algorithms that were proposed back then. So I'm going to talk a little bit about neural networks in here. And neural networks were actually first proposed back in the 1950s, but we really couldn't do much with them because of the constraints we had at that time. Now, we move out of that sort of, there's the first AI winter, it's sometimes called, in the sort of the 1970s and the early 1980s. And then, the early, the 1980s into the 1990s became sort of the next boom in AI systems. This is what we call the expert systems boom. So there was enough data, enough computational power at this time to be able to build AI systems that are based on what we call expert systems. So an expert system is an AI system where we design in the logic. So if we were going to build a self-driving car that had an expert system, we'd say, okay, a stop sign is octagonal and it's red and it has these letters on it. So we come up with a bunch of rules that we can put into a computer, and then the computer has to look for those rules, and then we can use the algorithm. This works fine for some systems. But for self-driving cars, you cannot enumerate all the rules that it needs to follow, right? But if we're trying to control like a building heating system, we can enumerate the rules, right? Okay, if the temperature gets above this, turn off the heater. If the temperature gets below this, turn on the heater, right? There's relatively straightforward rules, although it doesn't work perfectly even today. But yeah, you get the idea, right? We can design in these systems, and that only gets us so far. So at about the 2000s time, when the dot-com boom sort of ended, we entered the second AI winter. And we really, things sort of stagnated there. That's about when I entered grad school. And then in 2012, you can see all the lines go up then. So there was a paper written by a research student in Canada who discovered that he could use large amounts of data, which we were now collecting, and put it on a GPU, which is now widely available and very computationally capable to solve a really, really big complex neural network. And suddenly we discovered that can solve problems much larger and much faster than we could do before, and it just opened the doors, it opened the floodgates to really what we've done today. So the last decade or so has been extremely fast innovation in this space that I'll talk a little bit more about why that's happened. And I'm going to mostly focus on talking about the innovations that have happened since then. So it's worth talking about what can AI currently do and what can it do. I've given a talk or a variation of this talk, for the past 5 or 6 years, and I have to continually update this slide. Does anybody recognize that screenshot there from a few years ago? Jeopardy, right? Yeah, okay. Does anybody recognize the middle contestant there? Or any of the other contestants? I know it's kind of small. Ken Jennings, yeah. So Ken Jennings is there on the left. So Jeopardy had this tournament of champions with IBM's Deep Blue computer. And so that's the contestant in the middle, and it beat the pants off of the top contenders that they could bring in, including Ken Jennings, as a demonstration of, hey, here's an AI system that hundreds of IBM researchers, the smartest people in the world, spent thousands of hours to build to try to be two really smart people. So you could argue, are we really winning here? I don't know. But technically, yeah, we can build a system that can answer Jeopardy questions really well. If you take that system and put it in a car, it's going to be useless. In fact, IBM is famous for building this IBM Watson thing and branding it and then trying to use it in the medical field, and it flopped spectacularly. The AI system, they were able to fine-tune it for this sort of use case, but using it in a different domain is a completely different challenge. So the idea of transferability of learning across AI systems is still an unsolved problem. But we can still train specialized systems. So can we have an AI system that plays a good game of table tennis? Actually, yes. You can go out on YouTube and see all sorts of interesting videos of that. Already talked about Jeopardy? Yes, we can play a competitive game of Jeopardy. Can we drive safely along a curving mountain road? Yes, we can do that today. We could not do that a decade ago. Drive safely in general. That's an interesting question. This is getting better. It, I guess, depends on the definition of safety. But driving more safely than some drivers, sure. All drivers, probably not. Can you buy a week's worth of groceries on the web or predict the week's worth of groceries? Absolutely, yeah, we are definitely there. Discover and prove a new mathematical theorem. There are some cases where we have theorem-proving AI, but they tend to be more derivative works and not as much innovation going on there. So that's maybe not really there, and that's a hard problem. Can we have an AI system that can converse successfully with another human being for an hour? Maybe, yes. If you've ever called into one of those automated help desk systems, yeah, you press 3 for this, press 5 for that, and you finally get to a human being. I'm sorry to tell you, they might not actually be talking to a human being anymore. You might actually be talking to an AI-generated voice, and then they say, oh, I'm going to have to transfer you to my supervisor, and then you might actually get to talk to a human being. So you may have already been fooled by this. You may not have. But yeah, it's an interesting question to ask. How would you tell? What question would you ask that person to tell whether it's a person or not? Yeah, so you could ask that, right? But could we train an AI system that could make up a name of where it lives, right? So actually that question I just posed to you is the idea of the Turing test. If you want to learn more about that, it's a really interesting thing, but the idea that the Turing test is what questions would you ask a system that you cannot see or feel to know whether it's a real human or not. So yeah, so how are we going to know unless we see somebody? It's a good question. In fact, if you go to a drive-through at like a McDonald's or a restaurant like that, how do you know that the person you're talking to at that restaurant is actually in the restaurant? McDonald's already forwards most of those conversations to a central hub to take the questions, and there's no reason why they couldn't be automating those. In fact, it wouldn't be surprised if they're actively working on that. So yeah, so we are already being fooled. So that's why there's a question there, because it depends on the context whether we're actually being fooled. Performing a surgical operation. So this can be done. It's the pilot question, right? Are we going to let the AI make decisions like this, or are we going to still make sure that there's a human in the loop? And so we're not ready to let AI systems do that. But could it potentially, if we want to? Put away dishes and fold the laundry. Yeah, there are robots out there that do that. It'd be great to have one. They're not cost effective yet, but they do exist. Translate one language into another language in real time. This exists. This actually was proven a couple of years ago now. We've had the ability, you can speak into a system and have it speak right out in the other language. Write an intentionally funny story. So this is an interesting question. I asked ChatGPT to tell me a joke. This is what he told me. It said, why did tomato turn red? Because it saw the salad dressing. So ChatGPT can tell a joke. Okay. But then if you write in there, I don't get it, ChatGPT attempts to explain it. And I won't read all this to you, but this is what it says. The joke is a play on words. Tomatoes are normally red, but in this case, the tomato turned red because it saw the salad dressing. Saw can mean perceived visually, but it also can mean cut into pieces. Like how salad dressing is poured onto a salad, yada yada. So it's just kind of wandering off on its own journey, right? Okay, so it can maybe tell a joke, but can it explain the joke? No. Humor is it's a human thing. It's really a difficult thing to do. So I promised you I'd tell you about driving a car. So when did you learn to drive a car? 16, yes, that's a typical age, right? how did you learn? How did you learn to keep the vehicle on the road? What sorts of things? I mean, yeah. How did you figure this out?
Someone with you.
Say that a little louder, sorry.
You had somebody with you.
Yeah, absolutely, right? So you had that person next to you ready to grab the wheel or, put the car in park or whatever, right? Yeah, obstacles. How did you know an obstacle was an obstacle? Did somebody have to explain to you, okay, that's a sidewalk, don't drive on it, right? That's a stop sign, maybe somebody had to explain that, right? But you didn't necessarily have to be told all those things. One of the examples I like to think about is, what if we took somebody who lives on an island and is isolated from the rest of the world, and they're 16 years old, and we fly them over here and we put them in a car. Would they drive the car and learn how to drive the same way you did? No, right? Why not?
They don't have prior knowledge.
Yeah, so there's prior knowledge. So how early did you start learning how to drive a car? Yeah, so when my oldest son is 9 right now, when he was 5, I was driving, I don't remember where I was driving, doesn't matter. And he pipes up from the back seat. I thought yellow meant you're supposed to slow down, Dad. A 5-year-old has figured this out, right? He can barely read, he can do a little bit of math, but he knows that I'm breaking the laws of the road. So we actually start learning these things much earlier than you might think. And it's because it's a really big, complex task. There's a lot of nuanced things. So if we're going to design a computer and try to tell it how to drive, there's a lot of complex logic. So if we're going to design an expert system with all the rules to make these decisions, it's way too complex, right? You think about just all the signs we have to do, it's impossible. And yet, we have cars that drive themselves today. How do we get over this? Well, the early days of autonomy were actually sparked by a project by DARPA. So DARPA is the Defense Advanced Research Project Agency of the US. They issued grand challenges from time to time. In 2004, they issued a grand challenge to drive a vehicle 142 miles across the desert. And they gave a pre-marked path in GPS coordinates. And you can see one of the vehicles over there that was doing it, that a bunch of different universities and car companies entered. The first year of the competition, there's one vehicle, the vehicle that won, made it 7 of the 142 miles.
Wow.
And that was the winning entry. All the other vehicles just didn't make it out of the gate. If you look at the vehicles, they have millions of dollars of really big, complex sensors. There's a lot of complexity to these things to make them work. 1 year later, 5 teams completed the challenge. So in 1 year, there were, I think, a dozen teams that entered. We saw that innovation really quickly. Exactly. So we learned from our failures, came back and improved, right? And so what happened, DARPA took a year off. I'm not sure why exactly, but then they came up with this urban challenge. So there are 11 teams that competed in this. This is vehicles driving around an urban environment. It was a very controlled environment, but this was actually the first place where 2 autonomous vehicles had an accident. It was a very low-speed thing, but this was, you can see some of the entrants down here. So, Stanford, General Motors, Caterpillar, MIT, big players in trying to make these innovations happen. And 6 of the 11 teams were able to compete in not just an environment where there's no other vehicles. Now we've got other vehicles in the way and that kind of thing. But you'll notice some things about these vehicles. So, and I actually like to pick on the MIT vehicle that's in the bottom right here. It's a little bit hard to see, but way over here on the back, you might notice this white thing on top of the back of the vehicle. That might look a little bit familiar. If you've ever been in a camper or an RV, does anybody know what that is? It's an air conditioner.
Yeah.
It's a camper air conditioner sitting on the top of this really expensive SUV. Now, why would they stick a camper air conditioner on the top of this SUV?
Cool this stuff.
The back of this vehicle is completely full of computers, top floor to ceiling. They needed this to keep the back of the vehicle from melting down, basically. And so, the computational power required to take all the sensor input and make decisions based on this using these expert systems is really enormous. This took, again, dozens and dozens of really smart people, a really long time, thousands of hours to be able to build these systems. And ultimately, how was this done? This was done with lots of sensors and sort of brute force expert systems building in kind of logic. So how do we go from this to what we have today? Today we're using minimal sensors. We're just using, in many cases, just cameras and relatively low-cost sensors. Really relatively cheap computational hardware, and we don't have massive air conditioners sticking out. So what happened? The deep learning revolution happened. So we were able to develop these deep learning models that don't require us to specify exactly what happens in every situation. Instead, what we do is we give it lots and lots of data, lots and lots of examples of things, and we tell it, yes, this is good, this is bad, and let it learn on its own. So it's a completely different way to program computers, and that's really what we teach our students today, and what's driven this revolution. There's tons of companies out there now doing this. This is, any companies that aren't working on self-driving features are getting left behind, to be honest. So how is machine learning different than kind of traditional programming? So in a traditional programming world, we're going to take the data, so the sensor input, we're going to take our program that says if you see this, do this, if you see this, do that, and that gives us our output, right? In the machine learning world, this deep learning world, what we're going to do is we're actually going to take our data, so the sensor input, and we're going to take the output. So we're going to know, okay, in this situation you turn the steering wheel right, in this situation you press the brake. And we can gather that output from just watching people drive. We just hook up a computer, log the data as people drive, and voila, we've got our data and our output. We feed that into the computer, and then out of that computer comes a trained model. And then we can feed new data into that, and it will predict the outputs. So it's a completely different way of training these things, and it ends up giving us a lot more sophisticated and complex models. This concept of machine learning is what drives virtually all the innovation that we have today in AI. So talking about data, I want to give you a sense of what this data is with a cat picture. So one of the common things that we do in sort of training students in how to do this is we'll do a process called classification. So we want to classify, here's an example image, what is it? Is it a cat? Is it a dog? Is it a chair? Is it a house? And so what has to be done is everything in computing is done with numbers. So we have to take this image that you and I see as colors and fur and all that kind of stuff, it has to turn into numbers. So what a computer actually sees is over there on the right. It's just a bunch of numbers. And then those numbers, the output ends up being a confidence number in this case. So it's 82% confidence a cat, it's 15% confidence a dog, it might be a hat or a mug. You might think, oh, that's sort of funny. But then think about how many mugs are out there with pictures of cats on them, and how many hats have pictures of. So there's maybe a little bit there, right? It's, So machine learning is all about coming up with algorithms that allow computers to evolve behaviors that are based on empirical data. So it's the data that we collect, and then we evolve an algorithm that's based on that. That's why this is called machine learning. It's because we show it examples, and the algorithm learns. Just like, I show my 5-year-old an example of how to drive, and he learns the rules, right? Why is learning possible? It's because there are patterns in the world. You and I are hardwired and then learn past that hardwiring about what patterns mean what, right? If you get a waft of something that smells like fresh baked bread, you feel hungry, right? Potentially, you like bread. So why? It's because we've learned that pattern of that scent gives us the sense of what's going to happen, right? There's a pattern. Oh yeah, there's going to be fresh baked bread down the bakery. I should go check that out, right? These sort of making these connections is what allows animals to learn. If you've ever trained a dog, we have to have certain patterns that we do over and over and over, and that's how the way it works. If you ever learn math, you have to do lots of repetition. That's how you learn, right? And so that's the same thing with these AI systems. We have to show them lots and lots of examples. The difference is AI systems don't need rest, and we can scale them a lot faster and larger. And so that's what allows us to do more with them than biological systems. So stemming from a biological neuron, this is sort of the inspiration for how deep learning models work. So you have a neuron, you have neurons all over your body, that's how you sense the world. So imagine you have a candle that you put your finger over, you're going to feel that heat. What happens is those neurons, the receptors that are in your finger, are going to fire an electrical impulse that then goes to the next neuron, all the way up to your brain, and your brain is going to go, okay, that's a hot sensation, you should move your finger. And it will then send signals down to your arm to tell your muscles to move. You don't have to think about that. That's just all hardwired in. So we have these neurons that take inputs and make a decision and then either fire or don't. And so that's basically the way that our bodies and our neurological systems are wired. So we can actually leverage that same concept and then use math to make it work. So this is the only math I'm going to have on my slides here, so don't worry. But the idea is this is an artificial neuron, and how we wire artificial neurons I'll talk about momentarily. But the idea of an artificial neuron is it's just a math equation. So if you've had algebra, basically what we do is we have, in this case, 3 inputs. These 3 inputs correspond to, they're wired up to the inputs of our signal. So, if it's a picture that we don't know what it is, it's what are the light levels at 3 locations of the picture. If you have a giant picture, it's every single pixel, what are the light locations of those pixels. Maybe 1 for bright, 0 for really dark. So you send those in, you multiply them by weights. These W1, W2, and W3 are weights that the network learns. So these weights can amplify signals or mute signals. And so you learn these weights, and then you multiply and add those all together, and that gives you an output. So this output is basically what gets fed onto the next neuron. So what we can do then is we can actually have inputs of what all of our, what our data comes in. We can connect all these neurons together, and they're just a bunch of math equations, just a bunch of multiplies and adds. And then we connect them all back together at the end for an output. And that output then can be a classifier, like it's a cat or a dog, or it could be, okay, turn the steering wheel right or left, or it could be predict this next word in the sentence. The way we wire this up is sort of agnostic of that. It's all just math that goes through it. There's a lot of other sophistication that can exist in these things, but that's the basic idea of how we take inputs and feed them to an output. I'm going to show you an example of something that I've used for a number of years with my students. So this is a driving simulator that a game you can play on your computer. What we have the students do is they drive this car. You're just pressing arrows on your keyboard and forward, back for stop and go, right and left. You drive the car a bunch of times. I have them build a machine learning model. This is what it looks like. So I know I showed you a model here that showed just a couple of layers. Machine learning models that do like self-driving car things have lots of layers. So actually the input in this case is at the bottom. There are 3 input layers because we split images into red, green, and blue channels. So there's 3 sort of separations of them. And then we send those through a bunch of different layers. There's convolutions, a bunch of other stuff here. And then we have an output. The output is just the steering angle. We then, once we've collected a bunch of driving data, we then send it through this network. And what happens is initially this network, all those weights are completely random. We don't know anything about what they should be. So we start out with random weights, and we send examples through, and we get an answer out. And neural networks are confident in their answers, but they're often confidently wrong. So they're going to get an answer, and what we're going to do is, because we know from our training data what it should do, we can compare that answer it gave with the answer what it should do, and then we can actually calculate the difference. So we can say, okay, you should have said this, but you did this. Let's find how much we need to tune the weights to get them to get closer to that right answer. But you can't do that just for one example, right? You have to do it for all the examples. So there's mathematical ways we can go through and send all these examples through and then sort of tune the whole thing so that it gets closer and closer to the right answer. So we actually send all of the example data through multiple times to be able to get it to closer and closer to the actual answer. And so what happens is over time, the error of this system goes down and down and down. It starts with a really high error rate because it's all just random. It doesn't really know what it's doing. But as it trains, it gets better and better and better. And we can monitor this training over time, and we get to a system that then, I will show you, this is an example output for a vehicle in this game driving itself. We just drop the car somewhere randomly, and you can get a sense of the environment here, right? So we've got sort of maybe an asphalt-like road surface, but we've got some shadows. There's a bridge here that has a different road surface. This car is deciding whether to turn right or left to stay on the road. And even there was a little turnoff. It recognized enough of that edge to know, okay, don't go off that edge, right? Stay on this road. So so in a matter of about 2 minutes of training time, the students can collect the data and train this and have this car keeping itself on the road. Now, there are no pedestrians here. There are no other vehicles. So this is a very simple, constrained environment. Oh, there's no snow. There's all sorts of limitations to this. But You get the idea, right? So it turns out this isn't really that hard of a problem anymore. And it's an interesting question. What if we train this model and then use it in a different environment? So the next thing I have the students do is drop this same car model in a completely new environment. So what do you notice about this environment? What's different about it? 2 lanes, yep. What else? Yeah, so I'm hearing steeper curves and deeper shadows.
Trees.
Trees, yep, absolutely. More trees, there are cliffs. And this car stays on the road. Now, if you were a passenger in this car, would you be happy? No. But it doesn't crash. We're not falling off a cliff. That's good.
There's nothing coming at you.
There's nothing coming out. Right, we don't have vehicles. So an important thing to note here is this car is wandering all over the road, right? If there's a police officer, you get pulled over. Why is this vehicle not staying on the right side of the road? Think about what we trained it with. We trained it on the data up here. We had no center line, right? So we didn't have a center line when we trained it, and now we expose it to a center line. What does it do? I don't know. It ignores it. In this case, it might actually pay attention to it in some cases. So I'll show you an example of where Tesla cars can be defeated, or used to be able to be defeated, by putting stickers in a road. If they encounter environments that they haven't seen before, we don't know what they do. So it's really important that we test these AI systems in as many environments as we can, because unpredictable behavior is fine if it's a toy or entertainment. It is not okay if it's a medical system or a safety critical system, right? So what we do with how these things make decisions is critical, right? And so that's one of the important lessons from this. I want to talk a little bit about a field we call natural language processing. We've talked a lot about images and that sort of stuff. But you probably have heard about ChatGPT or large language models or generative AI. Natural language processing is a broad field. It's also been around for decades, but it's really an important field that's had a lot of innovation in the last 12 months and gotten a lot of press as well. So why is natural language processing hard? If I say fruit flies like a banana, what does that mean? It actually has 2 potential interpretable meanings, right? We can either talk about fruit flying across the room, or we can talk about fruit flies, the little, gnat-like insects that sometimes find their way into our homes. So there's what we call semantic ambiguity in this. We need context to understand which of these we mean, right? If we saw fruit flying around the room, we'd interpret it in that way. If we saw little insects buzzing around, we'd interpret it that way. And this is part of what makes natural language processing hard. We can't just look at one word at a time in isolation. We have to have context to be able to build meaning. So ChatGPT is one of the most well-known examples of a successful large language model. Although the engine behind ChatGPT has been around for well over 5 years at this point. Early versions of ChatGPT actually weren't chatbot. They were just they were a transformer. They wrapped it with a chatbot, and that's what made it really exciting and interesting. But within 5 days of launch, they had over 1 million active users, and today it's somewhere around 25 million active users per day. The data set they used, they basically went out on the internet and scraped everything they could find on the internet. They wrote some bots that just went out there and took all the text they could find anywhere. That includes all of Wikipedia, news, everything they could find. Although they did that all prior to 2021, so some things have changed now that you can get more recent data, but somewhere around 500 gigabytes of data, which is actually not that much data if you think about it. Like there are movies that are larger than 500 gigabytes, but it's all just letters. If you want to run ChatGPT on your own, by the way, it costs about $3 million a month in compute power. It's a really expensive service to run because there's a lot of math going on behind the scenes that's crunching the numbers to try to make all this work. So it's wildly popular. And if you haven't played with it yet, it can be very entertaining, as I showed you earlier in an example. But what has ChatGPT done? So ChatGPT became those first 5 days that got to 1 million users was I think that was in December of last year, something like that. And so since then, there have been all sorts of challenges. So it passed the Wharton MBA exam. Was able to pass the U.S. medical licensing exam. It got in the 37th percentile for the LSATs, so it's ready to go to law school, evidently. The uniform bar exam got the 90th percentile, so not only was it able to sort of be ready to go to law school, was able to get through the bar exam. It got a 1400 on the SAT out of 1600. And it passed a court sommelier, master sommelier exam, which is like, you'd think, well, you got to have all your senses for that. Evidently, they just wrote the exam very clearly. So it can do a lot, but I actually think these accomplishments are more emblematic of the weaknesses of those tests than it is of the ability for ChatGPT to demonstrate knowledge. In many cases, it's very capable and sophisticated and has a lot of power. But in many cases, it also is emblematic of just really poorly written tests. And so some examples here. So if you asked, this was done a little while back, so I haven't tested this recently, but if you asked, at one time, there was a group that went through and tested all these things. You asked ChatGPT, can coughing effectively stop a heart attack? It would say, yes, it can effectively stop a heart attack, which is absolutely not true. In a law question, what relative are you not allowed to marry in California? It says, you're not allowed to marry your first cousin in California, which evidently is false. So there are a lot of things that it can get wrong. In fact, there's this idea of hallucinations that ChatGPT had. I asked ChatGPT, who is Derek Riley, MSOE professor? And it said, I'm an associate professor of mechanical engineering at MSOE, and my research interests are in advanced manufacturing, robotics, automation, and engineering education. I teach courses in these topics, which I don't. I'm a computer science professor. I'm not a mechanical engineering professor. What's going on here is what's called a hallucination. So can you guess what the largest major is at MSOE? Mechanical engineering. So what it's doing is it's making a probabilistic, it's rolling the dice. Actually the way ChatGPT works is every word is predicted from the prior word. So it starts out with Derek and then says, what should the next word be? Well, it comes up with, the model predicts, here are all the words it could potentially be, and then assigns probabilities of their quality, and then rolls a dice. It says, okay, pick the one that's the highest probability, and Riley's the next one. So it forms these sentences one word at a time. It does have context, but it calls me a mechanical engineering professor because the highest likelihood of me at MSOE is to be a mechanical engineering professor. So it's not necessarily innovating as much as it is sort of finding often a common ground. But because it's rolling the dice every time, you're going to potentially get a different answer every time. In fact, very often you will. If you do this query now in ChatGPT, by the way, it'll usually just say, it doesn't do well with people. So it'll say, I'm not sure. Use Google or something, I'm not sure. So I've talked about some of these things, but it's a predictive model. It's just predicting that next word. It also has limits to how much data it can ingest, and it has limits to how much data it can see backwards. So you saw when it was explaining that joke, it can get itself off on a tangent and just kind of keep going. And you probably know people like this, by the way. It's not just a ChatGPT thing. You just kind of start talking, you're off on a tangent, and it's like, where did I start this conversation? ChatGPT does that too. So it's not just people, I guess. It can't search the web, so it's not able to pull up more recent facts. Although there are later versions now, and there are variants that can do that. And then, of course, it gives really overconfident answers that may be incorrect. And so there are also other interesting impacts. In the early days of ChatGPT, there were companies putting information in like, oh, hey, can you correct this schematic for me? Can you fix this, this wording for this thing? And as people are putting data into ChatGPT, the people, OpenAI behind ChatGPT, are collecting all that data to improve ChatGPT. But then there's proprietary data going into ChatGPT that now OpenAI has. So that's a problem. Students are using ChatGPT to write code and essays, and this is something that academics are scrambling to try to address. Personally, I think ChatGPT is a lot like a calculator. When calculators are introduced, I don't teach my kids how to add and subtract with a calculator, right? But if they're doing calculus, which they aren't yet, but when they're going to be doing algebra and calculus, it might make sense for them to have a calculator to help them be more effective at learning other concepts. So we want students to use ChatGPT when it's appropriate, but not in the process to sort of short circuit the learning step. Another example I've heard of this that I really like is, if you use a sports analogy, ChatGPT is sort of like, it will do all the weights for you, right? And so you could use ChatGPT to go do all of your exercise for you, but when it comes time to play the game, ChatGPT is not there to play the game for you, right? And so you need to do all of your exercise. You have to put the work in to learn the material so you can actually be effective and leverage it. So people use ChatGPT every day in industry. I think it has lots of really great use cases. Students can use it in the right use cases, but we're trying to figure out how to help students negotiate that because it is complicated. I don't want you to get the impression that all intelligent systems are infallible, and hopefully you leave here at least with that. I promised you the example of Tesla, so here it is. So there's a screenshot up there of the example from a paper of a way researchers were able to put 3 strips of reflective tape in the road, and it caused the vision systems on a Tesla Model S to believe that the lane was ending. And so the car at highway speeds, if it thinks the lane is ending, merges. And so, it's a tricky decision, right? If you suddenly discover the lane is ending, do you just crash into that barrier, or do you just merge in there whether there's a car there or not? There's some interesting philosophical questions about which you would do, but the decision the car made was just to merge over. And so whether there was another vehicle there or not. So they basically showed they could fool the vehicle with some strips of tape. So there's a lot of adversarial challenges that you can overcome, that need additional work to overcome. It's been shown that you can beat the Apple Face ID system with a mask, although the mask has to be like a 3D mask. It's really sophisticated, so it's not really a practical beat, but you can defeat that. There's a self-driving shuttle in Las Vegas that their first day of deploying them, they had an accident. There's in Texas, I think in Austin, they had there was a traffic jam of self-driving cars that people figured out how to call self-driving taxis over to a certain area, and then they started manipulating them and caused a traffic jam that nobody knew how to get rid of because there were no drivers. Microsoft had a chatbot that they released in 2016 that allowed online learning, and we've now learned that that's a terrible idea because people on the internet figured out, hey, this thing is sort of learning on the fly. We can start feeding it bad ideas, and within like 24 hours it was sexist and racist and was saying some pretty awful things. And so, so interesting stories. But another funny one, on the bottom right there, that's evidently pornography, according to a tool that the British police use to detect pornography in images. You can see it's a picture of a sand dune. So, but you can also imagine why that could potentially give a false positive, right? And then one of my favorites, so they developed an AI system to track a ball in a soccer game. So, and what it does is it actually controls the camera, and so the camera's supposed to be following the ball. I'll play the video here so you can watch what's going on. So it's a little bit hard to see where the ball is, but the camera keeps snapping over to this referee. So it's trying to put the referee in the middle of the frame. Can anybody imagine why this AI system is supposed to be tracking the ball, keeps tracking this referee? Could be the white flag. I think it might be something else. His head, he's bald. I can relate. So it turns out this is getting a false positive of a bald head. So they just may not have trained it with enough bald players, I guess. I don't know. So, these systems are not infallible. If they're not tested adequately and we, leverage them, they can easily go wrong. So we have to be careful with what we have. All right, time for Q&A. So I have a few minutes. What questions do you have? Go ahead.
Why do you hear so much about the danger of this to our society?
Yeah, that's a great question. I actually think the danger of AI systems is in the way that they're deployed. So I think there's a lot of enthusiasm around leveraging these technologies to make our lives better, right? We see this opportunity of hey, we can have, our radiologist can now review so many more images because we have these systems. And if we rush to adopting the technologies, we may miss some really critical limitations that they have. And so in the rush to adopt, we can run into problems, and we already have. I think that's one aspect. And the other aspect is around the fact that what drives all these systems is data. In the last 2 years, 80%, it's 90% of the world's data was generated in the last 2 years. This has been true for the past decade. And that's what we call exponential growth. And the question is, where is all this data coming from? Where is it going to? So you have apps like TikTok that really young kids are using, and they're feeding personal information. And you might think, okay, well, they could put in their name and that kind of stuff. That can be concerning, but what about their usage profile? How often they're looking at it? All of our cameras have phones on. Is your phone on right now? Is the camera on right now? How do you know? Right? They have microphones in them. Is the microphone on right now? You don't know. It actually could be collecting data. Whether it's collecting data or not is hidden in that end user license agreement thing that we all just click, okay, get me to using the app, right? So as a society, we don't really appreciate the data that we're giving away to be able to use these things. I think that's a big danger, right? Because when these kids are growing up now, they're potentially have this baggage of I pick on TikTok because it's owned by a foreign company. We don't know where that data is going. We don't know what they're going to do with that data in the future, and that potentially can be used for all sorts of malicious purposes. And so there's a feedback loop. We're collecting more data to give us better services, and the better services are giving us more data. And it's sort of unclear when this feedback loop is going to end. But I think there is a significant danger if we don't start to address some of these privacy issues that exist. Yeah.
The costs of AI are astronomical. I mean, for diagnosing diseases and stuff like that. What's your feeling? Does the good outweigh the bad, or is it level at this point? Or?
Yeah, no, I think in many cases, yes, it does. I think it certainly does. I think in a lot of cases, research is being done at such a rapid pace that we're not really asking, should we do it? We're asking, can we do it? And that's an important difference. I think if we ask, should we do something, it's a much more important question. Because there are many things we can do that we shouldn't do, right? And so a lot of the research in AI is being driven by, can we do something, and proving we can do something. And I really think that's an important distinction that's worth mentioning. But I think in the reality, there are many, many things where we can improve our quality of life for everybody if we can implement these systems appropriately. So I think we have to be more mindful of it. I think there's a lot of pitfalls and risk, and we have to be wary of the systems, and we have to look at them with a critical eye. This is not magic. It is, I like to think of it like gardening. What we're doing with these algorithms, we have to sort of feed and water them and maintain them. They're not really something that we can just magically expect to work and solve all of our problems. It's just a new tool that we can use that has the capability of potentially solving problems we couldn't handle before. The reason these deep learning systems can do this is because we've got a lot more data, and we have the ability to process that really large amount of data. So it basically just has a bigger brain that we can work with. And so that allows us to solve many problems, but not all the world's problems. So I don't know if that really answers your question, but it's a hard question. Yeah.
Mine?
Yeah, go ahead.
Well, I'm concerned about the math, because our country, our students aren't doing very well in math, and what do we rank, about 13 in the world in teaching math, and this takes a lot of math.
Yep.
And the other question I have is, how could this be used in politics?
Yeah, both great questions. So absolutely, I mean, we're seeing the effect of COVID and what happened in high schools in math. We're seeing lower performance in math than we saw before. I will say, maybe we're biased, but we have a lot of really high performing math-oriented students that are able to do a lot of this. But the reality is, this is available to everybody across the world. And I think the U.S. is still the epicenter of research in AI, but that will not remain that way forever. The more math education we have in the K-12 space, we're going to end up with more people who are capable of creating the innovations that our society needs. The political side of this is really is going to be messy. There are already fake ads and fake videos out there. So one of the things I talked a little bit about. ChatGPT is a generative model. It's inventing new things as opposed to like making a decision about driving a car. We have generative models that can create images, that can create videos, that can create audio. And so there are they're called deep fakes out there and you can use, you can find them for politicians, you can find them for actors, whoever, that show them saying things that don't exist. Our society isn't prepared for this yet. When you go to your bank account, you trust, if you go to your bank account, your website, you trust that website because there's a certificate process that ensures that if you go to your bank's website, you trust that that's their website. We don't have that for images or news or anything. And our society desperately needs that for us to be able to trust things. Right now, we sort of trust things based on, well, this friend sent it to me, or I saw it on this website. I mean, even really high-profile news organizations get it wrong. They have to go check their sources. Like, there's a lot of work to that, and the pressure to get news stories out quickly can override the importance of checking facts and sources. And I think we're going to run headlong into this year with the election. And I don't really know. I don't think anybody knows what's going to happen. But one thing I can hope for is that our society will demand a more robust system for verifying the accuracy and source of information. Because right now it's the Wild West, and it probably will be for this election cycle at least. Yeah.
So who is our society and who is in a position to make these decisions and so forth?
I think we are. I think we have to demand it. I think that's, the reality is, the only reason politicians ask is because either the lobbyists pay them to do something, which I can assure you they're not getting paid by people who are going to tell them to make this kind of change, or we as individual citizens can ask for this and demand it and expect it. I think we have to do that.
What do we ask for?
We have to ask for accountability in verifiability in sources. I think that's the key. Yeah, I mean, you have to know if somebody's giving you something that you can trust where that's coming from. And I think we will see new companies and new innovations around verifying the source of information. The same way that, when the internet started, there were new companies that came to help us verify that a website is the trusted website. They're certificate sources that are used internationally. So we have international organizations that have established that. But it took decades to get there. And we are starting from ground zero. There's really not much there to build on. So I'm not very hopeful that we're going to have the ability to identify trusted sources in the short term here. And it does not seem, I mean, some of the most flagrant spreading of these things happens on social media. There are trusted places you can get information from, but even those are, somewhat suspect. But the number of people and the amount of information that people rely on from social media is fueling the need for this. So I think that's the area where a lot of the misinformation gets promulgated. Yeah.
Do you have any opinion on Google's expert Bard? I've been using it now since it came out.
Yeah. No, Bard is very similar to ChatGPT. I would say also very capable. I would say it's not vastly better or different. It's a variant like ChatGPT. But I've heard positive things. I haven't personally used it a whole lot, but I've heard good things.
Bard knows who you are.
Oh, good.
And I think you got it right.
So
you can check it.
Okay, good. Yeah, Google has a lot more information than the OpenAI people. OpenAI is now partnered with Microsoft, who also has a lot of information. But this isn't stuff is changing constantly with these systems. They're really, it's an ever evolving field. So, yeah.
So do you see a time when when there would be sort of like an FDA organization regulating this?
That's an interesting question. We could go down the path of a federal regulator. I worry a little bit that the federal government doesn't move fast enough to stay on top of, you know, the rate of change of these things, I think, you know, we could go that direction. And I think it's worth pursuing that for certain aspects of this, but I think it's probably going to have to come from private industry and individuals demanding it and expecting it. I think it's hard for me to see how government will be anything more than reactionary. I think being proactive is a really hard thing for the federal government. Other questions? Yeah?
Climate disaster, is this potentially a tool that's going to be helpful?
Yeah, will this help or hurt us? Yeah. I mean, I hinted at it, but the models that we train for these things are extremely power consumptive. They're using huge amounts of electricity. You know, there's lots of rare earth metals and that kind of stuff that go into the chips that are driving these things. You know, although in the grand scheme of things, that sort of pales in comparison to lots of other effects that are negative impacts on the environment. I actually think it has the potential to be a net positive for our environment in that it can give us ways to find new innovations and to automate processes that are currently really inefficient. You know, we can use these AI systems to be able to do, and they're already actively being done, to do like surveys using satellite data to identify, you know, where is clear cutting happening in the rainforest. We can look at where is the garbage patch and target certain, you know, very concentrated efforts to do cleanup. Monitoring can be a lot better. You know, there's a lot of potential use cases that can make our world better that are spinning off of the innovations that are happening in this space. And I'd like to think that our society will continue to prioritize those, but it's up to the next generation of innovators where they want to take these things. So yeah, but I think it will be a net positive. I think it already is being a net positive, and I think the environmental cost of the power for these systems is I think it's just the cost of doing business. I think it will be widely outweighed by the benefits, but time will tell. Yeah.
What would motivate private industry to regulate itself?
The threat of the threat of bankruptcy. To be honest, like I think, you know, the only thing that motivates industry is private industry. I have a cousin who he's actually an alum of MSOE, and he once told me that he went to work for a company and his boss asked, you know, he worked for Texas Instruments. He said, okay, his boss said, well, what does Texas Instruments do? What are we here for? And he said, well, you know, we make semiconductors to do this and that. I said, no. We're here to make money. And we do that by creating semiconductors. And I think that's what private industry does, right? So I think the only way you get through to private industry is by threatening their source of money. So right now, if you look at the companies, you know, you have to look at the incentive. Like, why is a company going to, you know, why is a company like Twitter or Facebook going to allow a deep fake on their platform? It's because they get more clicks and more ad revenue. If we are not on that platform, if we're not clicking on those ads, we're demonetizing the incentive. Now, it's really hard for us to do that when we have such an uninformed consumer base, right? And so I think there's an aspect of educating our population that I think is critical, but really challenging to accomplish. And I'm not exactly sure how to do that. So it's a good question. Yeah?
Yeah, has anyone really looked at the implications for jobs in this country and
Yeah.
not all of the changes that need to be made, if they can be made fast enough so that there aren't more
Yeah.
people?
Excellent question. So what's already happened? Oh yes. So the question was, what's the impact on jobs? And I think, correct me if I'm wrong, but there are already impacts on jobs due to AI. What we're seeing is often, you know, AI systems will come in and affect a job. It'll often make people more productive initially, and usually these systems, what they're doing is actually removing some of the drudgery work. So AI systems tend to be really good at pattern matching. So they're looking for tasks that are being done over and over and over, like that call center, right? They're saying the same things over and over and over. So they're good at doing that sort of drudgery work. But to solve the hard problems, you still need people at the end of that line. So there are going to be some tasks that are going to be obsoleted because of this, right? But it's going to be that first call center person who's earning minimum wage. They're going to probably lose their job. Some of the white collar jobs that are going to go away, probably the first white collar jobs that are going to disappear are in the legal profession. And we're going to see those in the next decade. I think the legal profession is going to be vastly changed in the next decade. If you think about it, sorry if anybody's an attorney in here, but if you think about it, there's a lot of pattern matching and pattern recognition and repetitious behavior that exists in contracts and in law that can be automated. And the question is, how quickly will organizations adapt to that? And then what attorneys will have to do is they'll have to become specialized, right? To not solve the common problems, but to solve the really specialized problems. And the firms that do that well will survive, and the ones that don't will go away. So like LegalZoom is a company, a national company that you can go out and get paperwork created for you. They're already leveraging AI. And it's putting pressure on local legal firms. I met with one a month or two ago who was already starting to feel some of that pressure. So it's happening. So I think that's the most affected white collar jobs. But like doctors, there's a lot. I think there's a lot of talk about like truck drivers going away. That's going to be an extremely slow transition. I think that the legal transition will be much faster than even truck driving. Yeah. Teachers, maybe.
That's been going on for a number of years in the legal profession. They're called paralegals.
Sure, yeah.
And the paralegals will be the ones that are...
Yeah, that'll probably be, that's often what's going to happen, right? Yeah.
Since you work with a lot of mechanical engineers, could you speculate what are the big changes coming in the future of mechanical operations?
Yeah. A lot of the changes that are going to happen in the mechanical space are actually going to be driven by the ability to model things in the virtual environment and create new things in the virtual environment. So like, if you need to design a new fixture to build a widget, you can specify this is what I want it to look like, and generative AI systems can come up with potential designs, or you can sort of insert your expertise to help affect those designs. So I think it will help from a creativity standpoint. It will help test things out. You'll be able to generate designs, test them in the virtual space before you actually build anything physical. And then by the time you build something, it's fairly robust, and it's going to actually, I think, shorten the time from the design or concept into implementation. The last 2 summers, I've worked at Milwaukee Tool. And I can say already they are leveraging this sort of this increasing speed of design in both the mechanical and electrical systems to be able to innovate and get a product to market faster. They're doing things now that would have taken them, they can do it in a year that would have taken a decade before, just because these systems have the ability to work through the things that wouldn't work much faster and get to that solution that will work. And so I think, I see that as just continuing to accelerate. So I think it'll just continue to shave the time off of, hey, we have an idea, to, hey, here's the solution to that problem. And that's true in the mechanical space, in the building space, in the electrical space, and in virtually all forms of engineering. Excellent. Maybe one more question. Anybody has any? We've exhausted all the questions. Okay, excellent. Well, thank you for having me.